You are given an array of integers, nums. There is a sliding window of size k, which is moving from the very left of the array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position, return the max sliding window. So what exactly does this mean? This just means that we have a sliding window, so some left and right pointer, that points to some portion of this array. So right now we're just looking at this portion right here. And on every iteration, we are going to be moving this sliding window to the right. And we are going to be taking the max element in each one of these sliding windows. So in this one, it would just be 3. We move to the right. We can see that this element is now again 3. We move to the right again. We can see that this element is now 5. And then we take all of these numbers from these maximums and we just put it into an output array. So when it says the max sliding window, what it really means is that where the output is going to be an array of numbers. So before we start really getting into this, let's look at the obvious solution. The obvious solution is to just have this sliding window move to the right every iteration. And on every iteration, we just look at the maximum in here. And let's just think about that. Every time we move to the right, we would have n minus k movements, because the kth element, and we're moving it all the way to the right. So we'd have n minus k of these movements, and we would be checking through this array of size k times. So we'd have a big O of n minus k times k. So this would be our brute force solution, O of n minus k times k. So we have to do somewhat better than this. And looking at our constraints below, if our length of our input array is 10 to the 5, most likely our solution has to be some linear solution, some O of n. Otherwise, we will time limit exceed. So we need to keep track of the highest number within a sliding window, but not only that, but we need to keep track of some order of highest numbers within a sliding window, such that if we lose our highest number, we can default to the second highest number or the third highest number or the kth highest number. And for this problem, we're going to be using something called a monotonically decreasing queue. Now, this is actually something that I did not even know about until I started doing this question. This is one of those obscure data structures that, honestly, if you don't know, it's totally fine. You just have to know it for this question, and you'll probably almost never see it again. And to be completely honest, I have never seen this. I think I may have seen it once before, but I didn't know that this would be the data structure that we'd be using for this solution until I started looking up what some other people had done for this question. So what the heck is a monotonically decreasing queue? Honestly, ignore this queue portion. All we're going to be doing is we're just going to be creating an array that is going to be decreasing or equal to the previous elements. So an example of this can be 9, 7, 3, 2. And the operations that we can do with this array is that we can add numbers to the end of it. Let's say we wanted to add a 1 here. This is fine. Let's say we wanted to then add a 5 here. This is also fine. But when we add this 5, there's some operations that we need to do afterwards. We need to get rid of all elements before this that is less than this number. So we would end up with getting rid of this, this, and this. So what does this get us, or how does this help? This is something that we implemented, but this is just a data structure that we can continue to improve on. So instead of just putting the numbers here, let's also put the indices of these values. So instead of having something like 9, 7, let's have 9, 0, and 7, 3, and 5, 4. And again, these are just numbers that I'm making up. They're not in any example that are shown already. But this is perfect. This is exactly what we need. So long as we maintain our left and our right pointers, our sliding window, we can say, is this element in bounds, or is this something that we should get rid of? Because remember, our highest number is always going to be at the front, and we're going to be looking at only this number and saying, on every iteration, is this our highest number? Or do we need to get rid of this and check the next number in our queue? So let's start working on this solution. Let's start setting up some of the stuff that we had talked about before. So first, let's create that monotonically decreasing queue. Again, it's just going to be an array. So let's call this decreasing list. We know that our array that we're getting at first is going to have at least one element. So let's just set it equal to the first one. So let's just say something like nums 0 and then put the index 0. Again, this is just going to be the value, comma, the index. This is supposed to be in a tuple. What we want to do is we want to determine the max value on each successive iteration, but for the first k elements in our initial sliding window, we have to make a special case for this. So let's do this for the first k elements. We're going to say for I in range 1, because we already got the first element, to k, we are going to get the next smallest element. So next smallest equals nums I. And why are we calling it the next smallest? Because remember, we're going to be appending it to this list, and any numbers that are less than this number, we are going to be removing from the list. So again, this 5, when we added it to the list, we needed to get rid of these numbers before it. So it's safe to assume that we're always going to have the next smallest number. And what happens if we don't? We're just going to pop. So we're going to say while next smallest is greater than decreasing list, we want to get the last element, so -1, and we want to get the first element, 0. So again, this -1 just means that we're getting the last element in the list, and this 0 is just saying that we're actually getting the value. So remember, this is going to be the value, and this is going to be the index. Now, what are we doing? We are just going to be removing the last element if it is smaller than the next smallest element. So decreasing list dot pop, which will just remove the last element. Then add the next smallest, the index, and don't forget to put this in a tuple. Make sure that this is only going to be greater than, because if we had the scenario where it was 5, 4, 5, 5, we'd still want to keep this value in our list, just in case we're going to need it in the future. We don't want to get rid of this value. And just for an annoying edge case, we need to say this. What does this mean? It just means that if the list is empty, we are going to break out of this loop and not do a pop. This will just crash our program. And to really make this crystal clear, let's just do something like this. What this shows is that Python will evaluate some values for its particular truthiness. So an empty array will return false, whereas if we were to put something in this like 1, it would return true. So let's just give a quick sanity check on this. Let's just return nothing, and let's print out what we have. Forgot to put end here. So we got 3, 1 and 1, 2, which makes sense. For just this sliding window, we're going to say we have a monotonically decreasing queue of 1, and then we add the 3. But because we add the 3, we remove the 1, and then we evaluate the -1, which just gets put right at the -1. So we should have 3, 1. Yep, that's right where it is. And 1, 2. 1, 2. So great, we finally found a max value in that sliding window of k. So let's finally add that to our answer list. And let's just create a answer list. And then once we exit this loop, we're just going to say answer.append. And what are we going to add? We're going to add that first element in the monotonically decreasing queue, because remember, we're always going to have the highest value at the front. So we're going to say decreasing list 0 to get the first element. And then we're going to add the actual value from it, because this is the value, this is the index that it's at. And then we are just going to iterate through the rest of our array, doing pretty much the same thing. We just need to add some extra values as well. So let's make our while true loop. We're just going to make an infinite loop and create some condition to break out of this. We need our left and our right equal to 0 and k minus 1. So we're going to have our pointers starting from here and here. And then on the first iteration, we're just going to move left plus equals 1, right plus equals 1, because we already did this step here. We already evaluated the first sliding window. And now let's create our condition to actually break out of this loop. Let's just say right, when our right is greater than or equal to the len of nums, we're going to break. And this just means that once our right pointer hits the end of this, there's nothing more for us to do. So now on every iteration, we want to check to see if the first value in our decreasing list is going to be in bounds. If decreasing list, first element, index, if its index is less than our left pointer, then it means that we are out of the window now and we need to get rid of this element. So we're just going to say decreasing list dot pop 0. So before we had pop with nothing in it to remove the last element, but now if we use pop 0, that means we're just getting rid of the first element. And same as before, we just need to add a case where if this array is empty, we need to make sure that we don't pop, otherwise it will break our program. So just add this. So let's get our next smallest number. So next smallest equals nums of r, because it's just going to be the next number that we add to our sliding window. And what did we do before? We got rid of all elements for it that were less than it in the monotonically decreasing queue. So we just have to say now, while next smallest is greater than decreasing list, the last element, and its actual value, we want to say decreasing list dot pop. And the same deal, we just want to make that case where it is empty, then we'll stop popping. And then finally, we will add our next smallest value to the decreasing list, as well as its index, in this case, R. After we add, we just get the greatest element in the decreasing list and add it to the answer array. So answer.append decreasing list, first element, and get the value. So, and that should be it. After we break out of this loop, we just return answer. And let's see if this runs. Invalid syntax. Looks like it ran. Let's submit. All right, looks like it works. Let me just zoom it out just so y'all can get a better look at it. But yeah, that's all you need to do. So this algorithm will run O of n time because on the first part, all we're doing is we're just iterating through the first k elements. And then on the next part, we're just iterating through each element afterwards. So it's only going to have to do one pass to see all the elements and make a decision on how to give the answer. When it comes to size, the only thing that we're really using is the answer array and the decreasing list, which are always going to be a max size of k. So this final answer would be O of n runtime and O of k space. Now I do want to point out how mine is in like the bottom 5%. Honestly, this is fine. Don't get hung up on these. You can run this solution many times and you'll probably jump around a little bit. But what matters more is getting the optimal runtime and the optimal space in your solution. There are some things in here that we could do to make this a bit faster. For example, instead of using a array to use this, we can use another data structure called a deck, which is pretty much exactly the same thing, but this one's just more intuitive to understand. So don't get too hung up on this. All you need to know is that the runtime and the space are optimal. Please like, subscribe, and let me know in the comments which question I should tackle next.